Hi, Integrated Math 1. Welcome to lesson 2.1.1c. So we're on day 3 of connecting our arithmetic sequences to our linear functions. We're going to keep the party going today. So we've already used algebraic properties to prove the explicit formula for an arithmetic sequence is the same as the equation for a linear function. We've already looked at defining the characteristics of an arithmetic sequence, that first term and the common difference, and how they're related to the defining characteristics of a linear function, the y-intercept and the slope, although we're going to be playing with that more today. And we're also going to be starting to dig in on connecting the slope of a line to the average rate of change of a function. That's what we're going to start digging into a bit more today. We already played with it a little bit last time. We already talked about slopes last time. So just as a quick reminder, last time we did mention that for slopes, because remember slope is rise over run, right? And so we said, hey, that means our slope is the difference in our y-coordinates, subtract your y-coordinates, over the difference in your x-coordinates, and so you subtract your x-coordinates. So we brought that up before, but it's coming back at us again today. So key terms, conjecture, first differences, we've talked about those already, and average rate of change. We're going to talk about that some more today. So again, we know all the sequences are functions. We now know that our arithmetic sequences give us linear functions. So let's start connecting all of this. Constant difference, slope, average rate of change, they're all connected. So in the last activity, you determined that the constant difference of the chair heights and the slope of the line were both equal to 8 inches per chair, right? We were stacking our chairs and we're like, hey, our constant difference is 8. And then we realized when we put it into function form that it was a linear function with a slope of 8, that our constant difference and our slope were the same. So is the slope of a linear function always equal to the constant difference of the corresponding arithmetic sequence? So we're going to do just a little bit of work. We're not going to go too crazy with this. But let's consider the graph of the arithmetic sequence represented by the general linear function f of x equals ax plus b. So here's my lovely graph, f of x equals ax plus b. So if I have n and then the next term and the next term and the next term, so term, let's start by identifying the constant difference of the sequence in the graph. Well, let's see, to get from here to here, that's like 1 unit, right? And that means that this is going to be my constant difference, isn't it? So I'm going to go over 1 up d. Ooh, sorry, now my writing's in the way. Let me get my writing out of the way because now it's in the way. So we go over 1 up d, over 1 up d. Now remember, the slope is rise over run. So that means we've got our common difference, d, right? We added 5 we add 8, add 8, add 8, add 8. So it's our common difference. And of course, we're only going over 1. So it looks like, sure enough, your slope is the same thing as your common difference. Or in this case, they used an a, but we can say that a is the same thing. D over 1 equals our common difference, d. So, yeah, that slope, a, is equal to the constant difference, isn't it? This is important. Another name for the slope of a linear function is the average rate of change. So slope is the same thing as average rate of change. And you're going to hear that a lot in future math classes. So whenever they're talking about the average rate of change, we're just talking about the slope. Now, because I'm using function notation, earlier we said that slope was subtract your y's on top, subtract your x's on the bottom. But now we're saying, so if I have 2 points, right, and I don't know, so points x2, y2, and x1, y1. Sorry, my pen went crazy. I'm going to erase that and fix that and make it better. So x1, y1. So we said that if I have 2 points, that I could subtract the y's on top, subtract the x's on the bottom, that would give me my slope. Sorry, my lights. You know how it goes in here. The formula for the average rate of change looks like this, though, when you do function notation, because look, instead of x's, I have s and I have t. Notice if I plug in an s, it's f of s. If I plug in a t, I get f of t. So again, I would subtract my F's on top, right? Those are my outputs. So to find my average rate of change, I would subtract the F's on top. Those are my outputs. Subtract my outputs on top. That's my rise. And subtract my inputs on the bottom. That is my run. So this represents the change in output. As I go from S to T, this is my change in output. But check it out. It's the same thing. I'm subtracting my outputs on top, subtracting my inputs on the bottom, right? Subtracting my Y's on top, my X's on the bottom. These are the same. It looks a little different. It looks a little different just because we're using function notation here and we're using our traditional X's and Y's there, but it's the same thing. So yeah, the slope formula and the average rate of change formula represent the same ratio. They do. The average rate of change, it looks all fancy because of function notation, but it represents the change in our output values to the change in the corresponding input values, right? Subtract your outputs on top, subtract your inputs on the bottom. The slope formula does the same thing. It represents the ratio of the change in our dependent quantities on top to our independent quantities on the bottom. But we know dependent is output, and we know independent is our input. So these formulas represent the same ratio. They're both slope. Sometimes we call it slope. Sometimes we call it average rate of change. Sometimes we use this formula. Sometimes we use that formula. It's all the same stuff. So let's take it back to activity 1, which we did a few days ago, right? We did this activity a few days ago where we matched up our explicit formulas with our graphs. Remember this? And we already played with graph C and the formula that went with it. So let's look at the others, graph A's, B, and D, and the formulas that went with them. We're coming back to those guys. So I have a few things I'd like you to do. First, for each graph and arithmetic sequence, can you just identify the constant difference in the explicit formula and on the graph that's easier to find on the formula, obviously. So go ahead and just find the constant difference for A, B, and D. Hit pause, write it down, hit play, keep going. So graph A is this guy right here. I can see my constant difference is a -4, so I'll put D equals -4. For graph B, this is the formula that went with it. I can see my constant difference is 2, so I'll write D equals 2. And for graph D, here's the formula that went with it. I can see that this one also has a constant difference of a +2, so I'll write D equals 2. Now, can you now take each of these formulas, and again, we're taking it back to a couple days ago. Can you rewrite each explicit formula in function notation? We did this a few days ago. I just want you to do it again with these other guys. Go ahead and hit pause to write your explicit formula in function notation, and then hit play when you're ready to check your work. So I'm going to start with graph A. Here is my lovely formula. I changed my A to F. Right? That was something we did. We changed A to F. And actually, I'm going to do two things in one. So I'm going to change my A of N to F of N. And don't forget, we're also going to distribute. So I'm going to distribute. Oh, I'm losing my pen. Sorry. So instead of A sub N, I have F of N. -4 times N is -4N. -4 times a -1 is a +4. And then I'm just going to combine my like terms and put my N up front. So my -4N is going to go out front, and 2 + 4 is 6. Okay. For graph B, I have this lovely formula. We'll change our A to F, and then we're going to distribute that too. So 2 times N is 2N. 2 times the -1 is -2. Yay, my A became an F. Like terms, -4 and the -2, those go together. And of course, my N needs to get pushed up the front. So now F of N equals 2N, and -4 + -2 is a -6. Last but not least, graph D came with this lovely formula. So I'm going to change my A to an F. I'm again going to distribute my 2. So 2 times N is 2N. 2 times the -1 is -2. Again, I'm going to move my N up the front, and I'm going to combine my like terms. A +4 and a -2 is a +2. So I have f of n equals 2n plus 2. You guys did really well with these the other day. Of course, just watch your negatives. You know that's an issue. You know it's an issue. It's a problem. But now my lovely explicit formulas are, of course, in function notation. Awesome. So now that they're in function notation, can you just verify real quick that that constant difference you found earlier is the same as the slope? So can you write down what the slope was for each of those function notations that you just wrote and make sure it's the same as your constant difference? Hit pause, write it down, hit play to check your work. So real quick, I'm just going to come back here. Graph A, it looks like my slope is -4, which is the same as my constant difference. Yay! I did a little extra work here. You didn't need to do the extra work. For graph B, if I come back to the other page, I can see that my slope, my slope is 2. There it is. My slope is definitely 2. And my constant difference was also 2. Graph D, yep, there it is. My slope is 2. And again, my constant difference was 2 as well. I did a little extra work here. You didn't need to do this work. I was just looking at what we wrote for our functions. So sure enough, our functions have the same slope as the constant difference that we saw earlier. We had this issue before, right? How is that first term in our explicit formula related to the y-intercept of the function? There actually is a relationship there. There is a relationship there. Go ahead and hit pause and jot down if you can figure out what that relationship is. They're not the same, but they are related. Hit pause to jot down if you can figure out what that relationship is, and then hit play when you're ready to check your work. Now, we said that our first term was the same thing as f of 1, right? If you plug in a 1, that's what you get. But we said that our y-intercept was what you get when you plug in 0. So here's how I thought of it. I realized if I took my first term and I subtracted my common difference, that would actually give me my y-intercept. So f of 0 is how we wrote it, but you can also make a little note here. That's our y-intercept. So that means for graph A, if I took my first term of 2 and I subtracted my common difference of -4, that gives me a +6, which was my y-intercept on graph A, wasn't it? For graph B, similar idea, I took my first term, -4, I subtracted my common difference of 2, and I got a -6, which was my y-intercept on the function notation for graph B. For graph D, I can take my first term, subtract my common difference of 2, and I get a 2, which was the y-intercept on our function last time. So there is a relationship between my first term in an explicit formula and my y-intercept of my function. Turns out you just got to subtract your common difference in order to find your y-intercept from the first term. There is a relationship there. Now, we've been talking about Kenyatta, and how this all started was her flowers, right? She planted all these lovely flowers. She was measuring how much her flower pot was, her sunflower was growing each day. But she's a cat. And we all know that cats love to knock things off of shelves because that's a thing that they do. Trust me, I know this. Kenyatta's cat loves to knock over flower pots. So each morning, she counts the number of flower pots her cat knocked over during the night before she uprights them again. So sequence C represents the number of flower pots knocked over on day 1, day 2, etc., etc. So you can see day 1, Kitty knocked over 3 flower pots, and again, 3 flower pots on day 2, day 3, day 4, day 5. Hopefully you're noticing something here. Real quick, can you determine the constant difference and write an explicit formula to represent sequence C? I know that sounds weird, but do it. Go for it. Go for it. And of course, don't forget also we're going to fill in a table and we're going to graph it as well. So start by writing the explicit formula, then go ahead and fill in your table and graph it. Hit pause to work this out and hit play when you're ready to check your work. So I don't know about you, but I was looking at this and I was like, oh, look, we're adding 0 and adding 0 and adding 0 and adding 0. My pattern is that I'm adding 0. So I said my constant difference was 0. And of course, my first term is 3. So when I set this up, I said, all right, well, a sub n equals 3 plus 0 times n minus 1, because that's my constant difference. And then I realized that 0 times anything is 0, and this whole thing cancels out. So a sub n equals 3. So if I fill in my table, day 1, 3, day 2, 3, day 3, 3, day 4, 3, day 5, 3. Yeah. Okay. And that means if I were to graph these, so if I was like, all right, here's day 1, 2, 3, 4, 5, and if I were to count up 1, 2, 3, oh, well then, day 1, 3 pots are knocked off. Day 2, 3 pots are knocked off. Day 3, 3 pots are knocked off. On and on. Okay, so we have the explicit formula. Can you write it in function notation? And maybe instead of using an f, let's use c. So instead of f of x, let's call it c of x. And instead of n, let's use an x. Go ahead and hit pause to put your arithmetic explicit formula into function notation, and then hit play to keep going. Well, earlier we were like, oh, hey, it's a sub n equals 3. And I said instead of using an f, let's go ahead and use a c. And instead of n, let's go ahead and use an x. So instead of a sub n, I'm just going to call it c of x. Do you notice something? Probably already noticed it. It is a linear function. It is a linear function, but you can be more specific. This is a constant function. Yeah. This is a constant function. My slope is 0. The y-intercept is 3. Yeah. Prove that the slope of c of x is equal to the common difference of sequence c. Hit pause, write it down, hit play to check your work. So you probably felt silly, like even writing it down. But yeah, the ratio of the change in output to the change values to the change in corresponding input values, it's 0. It's not changing. The output is not changing. The output is not changing. So yeah, our slope and our common difference are both 0. Output's not changing. Cat's just knocking down 3 pots a night. Poor little flowers. Do something about that cat. Here's a very similar sequence. Here we go. Sequence D, -5, -5, -5, -5. And given what you just saw with our flower pots getting knocked over by the cat, write me a function, d of x, to model the sequence. Hit pause to write it down, hit play to keep going. Well, hopefully you noticed that last time it was 3, 3, 3, 3, 3, 3, 3. So we were like, c of x equals 3. I wonder if the c is because it's a cat function. For this function, we've got -5, -5, -5, -5, -5, sequence D. So fine, I'm going to say d of x equals -5. Hey. You want to prove that it's a constant function? You know it's a constant function. It's a constant function. Why? What's making this a constant function? Hit pause, jot it down, hit play to keep going. So d of x is a constant function because the slope is 0. I have a 0 slope. I have a 0 slope. The values of the dependent variable remain constant. They don't change. They don't change at all. Before we get too far gone here, I don't want to just like spring things on you. Please, please, please remember that you can find the average rate of change, except I can't write, the average rate of change, you can find it, that's code for slope. Please remember the average rate of change is code for slope. So if you're asked to find the average rate of change, you just need to pick 2 points. I don't care which 2 points. Pick any 2 points that are on your table or any 2 points on your graph. I don't care. Pick 2 points on your table, 2 points on your graph. It's up to you. And then you can just subtract, right? Subtract your y values on top, subtract your x values on the bottom. Anytime you're asked to find the average rate of change, that's all you gotta do. That's all you gotta do. So as always, I hope you found this helpful. I hope you found this useful. If you've got questions or concerns, let me know. Come see me during office hours. Come see me at lunch. Email me. You know how it works. I'm around. All that good stuff. And I'll see you guys soon. Bye.